as we go into the biochemistry, which I know we're going to have Cyrus talk about, you'll understand why the low-fat component is so important.
So let's talk about what happens conversely on a low-carb, high-fat diet, which is kind of the reigning protocol for people that have this condition.
It is.
Either ketogenic or very low carbohydrate.
You can't talk about diabetes and not talk about the ketogenic diet.
100%. No question about it. Okay, so let's suppose that you're eating a low carbohydrate diet. So what that means is that you're going to be eating a diet that contains somewhere between, call it 70 to 85% fat in your diet, and then the remainder is going to be fat, protein, and carbohydrate. So a low carbohydrate diet has been sort of talked about, for 30, 40, 50 years at this point. At this point, we're now in the ketogenic diet. And the ketogenic diet is basically considered a very low carbohydrate diet. So what that means is that the total number of carbohydrates that they suggest per day is 30 grams per day, maximum, divided between breakfast and lunch and dinner. So you're eating 30 grams of carbohydrate plus more than 150 to 170 grams of fat per day. So again, we're looking at like an 80% fat intake, then a small amount of carbohydrate and the remainder in protein, okay? So in that situation, when you eat a low carbohydrate diet, you're effectively eating foods that are high in fat, medium in protein. And the fat molecules that are coming inside of your mouth, they're actually locked up as triglyceride in the food that you're eating. So triglyceride literally means glycerol backbone with 3 fatty acids attached to it. So you're eating, a lot of that triglyceride. It comes down your esophagus, it gets into your small intestine. In your small intestine, the glycerol backbone is removed from those fatty acids. Those fatty acids then go through the wall of your small intestine. They get into your lymph system. Your lymph circulates it into your blood. And then from your blood, they circulate in these particles called chylomicrons. Chylomicrons are particles that can basically deliver these fatty acids to tissues. So you eat it, they get inside of your blood. Now, these chylomicrons are basically trying to give fatty acids to tissues. So if 100% of those fatty acid molecules ended up inside of your fat tissue or your adipose tissue, then diabetes probably wouldn't exist today. The problem is that those fatty acid molecules, a lot of them do get into your adipose tissue, which is where they belong. It's a perfectly designed storage warehouse to absorb fatty acids from the blood when they're available. But in addition to getting inside of the fat tissue, they also get inside of your muscle. They also get inside of your liver. And that's okay if the total quantity of fat in your diet is maintained at a low level, like Robbie was saying, 10%, 15%, maybe as high as 20%. Okay? But when you're eating a ketogenic diet, again, you're eating 70, 80% fat in your diet. And as a result of that, the amount of fat that gets partitioned inside of your muscle and inside of your liver starts to grow over the course of time. So today you store a little bit, tomorrow you store a little bit more, the next day you store a little bit more, and over the course of time, now your muscle and liver have become effectively fatty acid storage depots in addition to your adipose tissue. So your muscle and liver are designed to store small amounts of fatty acids, and inside of each cell, they have this thing called a lipid droplet. The lipid droplet is effectively where the fatty acids or lipid soluble compounds congregate together. So this lipid droplet starts to grow over the course of time within each liver cell, within each muscle cell. And effectively that cell gets into a high energy state where what it's trying to communicate is like, wow, I have too much stuff inside of me. This lipid droplet has grown. Each one of these fatty acid molecules is 9 calories per gram, and it's a very energy dense molecule. And so the cell effectively says, okay, wait a minute, we need to go into self-defense mode here, and we need to prevent more stuff from coming inside. So if it were able to block more fatty acids from coming inside, it would do so. The problem is that fatty acids can easily get inside of tissues. They can easily get inside of your liver and your muscle, because the mechanisms to get fat inside of there are not very highly regulated. So because these tissues can't really block too much more fat from coming inside, what they can do is they can block the ability to communicate with insulin, because the insulin is a molecule that's mainly designed to allow glucose to enter tissues. In addition to that, glucose can also signal fatty acids and amino acids to come into tissues, albeit just a little bit less powerfully
insulin
than glucose. Yes. Right. So what the cells do is they basically say, all right, listen, what if we were to just shut down this insulin signaling pathway? Because if we did that, then When insulin comes knocking at the door, we can basically block pretty much all of glucose from coming in, and we can also block a small amount of fatty acids and a small amount of amino acids from coming inside. So intracellularly, this lipid droplet starts to create a traffic jam. And this traffic jam, basically goes into the inside surface of the insulin receptor and starts to alter some of the proteins that start the insulin signaling cascade.
On the surface of that cell.
On the inside of that cell.
Okay.
Yeah. So the insulin receptor is kind of like out into the surface and, in the extracellular environment, interacting with insulin. But then when you cross the cellular membrane on the inside, there's a whole bunch of, there's another motif in that protein. And if you alter the way that protein functions or alter any of its downstream signaling molecules, then you can basically shut down or strongly inhibit the action of everything underneath it. So it's basically just a game of dominoes. Let's just like alter the first couple so that nothing else beneath it functions properly. So this lipid droplet ends up causing a problem and impairing insulin signaling. So as a result of that, the next time that you go and eat a banana or you have a bowl of quinoa or some wild rice as an example, that's carbohydrate-rich food. Those carbohydrates enter your digestive system. Those carbohydrate chains get broken down into glucose. Glucose is now in circulation inside of your blood. Glucose has to be accompanied by insulin in order to get inside of tissues. So insulin comes knocking at the door, says, hey, knock, knock. I got this glucose. Do you want to take it up? And the cells respond by saying, we can't take it up right now. Sorry. We got all this lipid that we got to take care of first. Or some of the cells can't even hear insulin because they've shut down the entire signaling pathway. So as a result of that, insulin's knocking, it's knocking, it's knocking, it's knocking, saying there's no response, knocking, no response. So as a result of that, the glucose gets trapped inside of your blood.
Right.
So you have literally one banana. And then you go check your blood glucose 2 hours later and you look at the number and you're like, 245? I only had one banana. I guess bananas are bad for me. See, every time I try and eat fruit, my blood glucose goes high. Every time I eat potatoes, my blood glucose goes high. I guess those foods are bad for me. I should eat less carbohydrate-rich food.
So when that glucose is trapped in your bloodstream with the insulin and the cells are sort of refusing to uptake it, does that then prompt additional insulin secretion? So the insulin then continues to build in the bloodstream? Like, what is the downstream impact of that, and how does that relate to insulin resistance?
Yeah, someone knows his biochemistry. I like this. I like this.
Good. Trust me. I'm winging it here.
No, this is great. So yes, in that situation, what we just described, that is classic insulin resistance, right? So like we talked about earlier, insulin resistance can progress into prediabetes and then eventually to type 2. So in that state, if you've developed this level of insulin resistance, a small amount of insulin resistance, then the beta cells inside of your pancreas are saying, you know what? The insulin that we just manufactured and secreted into the blood, it didn't really do much. Let's make more. So then they go into sort of overproduction mode. And instead of making, call it 5 units for a given meal, they're going to make 7 units. And that happens today. And maybe those extra 2 units, they go and they get the